Okay, I think I am recording. Cool. Play from current slide. Okay, hello everybody. Welcome back to lecture 23 on volcanoes. Okay, let's get started. Again, chock full of slides. I'm going to actually set a timer this time so I can keep track. Okay, there we go. So this has a lot of videos and links for you to explore, click on in your own time, showing different types of volcanic eruptions, more about volcanoes, volcanic hazards, and that sort of thing. So click on these after the lecture when you can. Okay, what is a volcano? So, volcano is a mountain constructed by the eruption of molten rock. Okay, so they're basically mountains filled with lava or magma, and they are caused due to plate tectonics and mantle convection. So you will find volcanoes anywhere you find a plate boundary. You will find some volcanic activity, except for transform, as we know, that does not produce volcanoes, but convergent, divergent boundaries absolutely will cause volcanic activity, as well as hotspots, which is not a plate boundary, but it is mantle convection. Okay, there's some pictures in here. I'm going to flip through them. This is a picture of, I believe, Mount Vesuvius in Pompeii. A nice, scary picture of a volcanic eruption in Pompeii. Okay, so a little bit of review. Why did we spend so much time the first several weeks of class talking about magma and the different types of magma and where it forms and why it forms the way it does? This comes directly in play with volcanoes and the different volcanic activity you will have, the different volcanoes you can produce, and the different types of eruptions that you can have all come back to the types of magma and the composition that you have. Okay, so a little bit of review. Partial melting of crust produces blank type of magma. Partial melting of mantle produces what? Okay, so I'll flip through. Partial melting of the crust produces felsic magma, right? Because you're incorporating all of those silica-rich minerals and rocks into the magma through assimilation and fractional crystallization. You get felsic magma. So you get a magma that's lighter in density. It's more silica-rich. Partial melting of the mantle produces a mafic magma, right? So a direct mantle source will produce more of a mafic, rich rock or magma. Okay, so that's a little bit of review. Okay, continental crust requires a lower temperature to melt than oceanic crust. Partial melting of continental crust produces a felsic magma. Again, so this is a review on magma composition and how these different types of magma forms. Okay, so felsic versus mafic versus intermediate. Okay, you're going to have felsic magma in continental types of settings. So when you have a ocean to continental convergence setting, you're going to create a felsic to intermediate type of magma. When you have a tectonic setting in a divergent zone, or anywhere that you have oceanic crust, so let's say you have a hot spot in the middle of an oceanic plate, you're going to produce mafic magma. Okay, so the differences between the two and where you might find those different types of magma. Okay, so eruption style. Will it flow or will it blow? Okay, so this is the difference between a Hawaii style eruption and a very large explosive type of eruption like let's say Mount Etna or Vesuvius. This is also controlled by magma composition. Okay, so effusive eruptions are mostly basaltic, which is shown in this nice diagram here, or this picture. That's a Hawaii eruption. An explosive eruption you will see in this Mount Etna, Italy eruption. So again, different types of magma will produce different types of eruption. So effusive, effusive versus explosive. Okay, so the differences between those two. Okay, so why do we have effusive lava or magma in basaltic versus explosive in rhyolitic or granitic type of magma? This is purely dependent on the viscosity and the type of volatiles that you'll have in the magma. Okay, so a basaltic type of magma is really low viscosity, and felsic magma is really high viscosity. So we're going to look at that in a little bit more detail. So viscosity is resistance to flow. Okay, so the lower the viscosity that you have, the easier your material will flow. So this is a cool diagram showing the different types of viscosities and the different resistances to flow. So you have, where is this? Basaltic lava or magma. Okay, this is a very low viscous type of fluid. So you can imagine that it's the equivalent of corn syrup or peanut butter. It's definitely thick, but there is a flow to it. So probably not the really thick, crunchy type of peanut butter, but maybe the creamy type or corn syrup. You have this thickened material, but it's able to flow, it's able to move. Okay, whereas you have rhyolitic lava. Okay, so this is our most felsic type of magma. This is on the scale of tar. Okay, so you can imagine that it's definitely can move, but it's extremely difficult to move. So these types of magmas are going to be controlled by the viscosity. Okay, so basaltic being a lot easier to flow, to move, and rhyolitic being almost tar like inconsistency. So very, very difficult to flow. So you won't really ever get rhyolitic or granitic lava flows, right? So that's why you see these really incredible videos of lava or magma flowing as a river, right? Those are almost always 100% going to be basaltic lava, right? Because those are the types of lava that can have a flow to it. Whereas rhyolitic lava is not going to flow. It's going to be really, really, really high viscous, almost like tar, okay? And so when you have this really high viscous material, you're going to get a lot of gas being trapped in this magma or in the lava. Okay, whereas in basaltic lava, gases can escape easily. So a lot of gases are produced in volcanoes. In any type of volcanic setting, you're going to have some gases escaping, a lot of methane, a lot of sulfuric types of gases. When you have this really high viscous magma like tar, you can imagine that the gases are going to be super hard to escape, okay, because it's so thick, it's so sticky, okay, whereas in basaltic lava, these gases can escape a lot easier. Okay, so this is going to play into, is it going to blow or is it going to flow? Okay, so let's look at that in a little bit more detail. When you melt the crust, so our continental felsic crust, you're adding all of these volatiles and gases. So typically, our felsic lava is going to have more volatiles, more gases in it, just because of the nature of the magma itself. Melting of the mantle, not so much. You're not going to get as many gases as you are going to have with felsic. So not only are the gases being trapped by the felsic lava or magma, but you're producing more just in nature because of the melting of the crust. You're already adding all of those volatiles to the lava and magma, okay? And then you're adding the fact that you can't have these gases escape because it's such a sticky material, okay? So this creates a really explosive type of environment, whereas mafic already has generally less types of gases, but the gases that are produced are easily able to escape. Okay, so how do gases affect magma? You can picture this explosive type of magma or lava likened to a soda can, right? So when you open a soda can, right, you're releasing all of these gases that are under pressure, right? You have all of these gases that are under pressure. If you shake that can and then you open the soda, you're going to get this explosive type of soda eruption, right? That's kind of what's happening with our explosive types of magmas, right? You have all of this gas that's being trapped in the volcano. It's sticky. It's holding these gases back. When these gases accumulate enough, it's going to explode in this explosive type of volcanic setting. Right, so under less pressure, gas forms bubbles. Dissolved gas is held by magma, in magma by pressure. Okay, and then it propels the eruption and forms ash. So the difference between a high gas content, again, with our soda analogy, versus our low gas content. So the difference between opening up a soda can versus the difference of opening up a bottle of Gatorade. Okay, it's not pressurized. Gas is not trapped. So when you open up the Gatorade, a little bit of gas is definitely going to escape, but it's not going to be this pressurized gas content that you would have in a soda can. Okay, so this is another diagram just showing that, right? Explosive versus effusive, right? You have our explosive in our felsic or intermediate type of magma and lava, and then you have effusive in our basaltic. Okay, so it all goes back to the gas content and the viscosity. Okay, so just another slide showing this. These are some YouTube videos showing the differences between explosive versus effusive. So click on those, check those out, so you can actually see the different types of eruptions. They're pretty neat. Everyone loves seeing a good volcano erupt. Okay, but here's some pictures of what these eruption styles can look like. Okay, so you have an effusive eruption here, right? You see this river of lava. It's able to flow really great distances away from the volcanic source, right? Because of that viscous material. It's not as viscous as felsic lava or magma, right? So it's going to be able to flow greater. So now you can have a nice river of lava, nice basaltic river. Okay, versus our explosive eruption, again, these are going to be our huge Big Bang explosions, right? These are very viscous, high silica content, causing catastrophic eruptions. Okay, and these are in our felsic and our andesitic compositions. Okay, these are just some fun, different eruption styles. You don't have to know the names of these, obviously, but they're just cool to know that they have names. Strombolian, little burps of magma. There's some videos that you can check out. These are mostly in basaltic flows. So you have little burps of lava fountains erupting in this manner. You can get convection clouds. This is the type of cloud that you can get at Mount Vesuvius, where people write stories and recorded in history books, right? This has also happened at Mount St. Helens in the 1980s. Okay, this huge convection cloud of material. You can get this type of eruption that happens in shallow seawater. So this is kind of a steam explosion. It's when seawater is steamed pretty rapidly and explodes in the surface in a really shallow marine environment. Okay, so now let's look at the different types of products that you can get coming from your volcanic eruptions. So we have lava flows, pyroclastic debris, and then you have gases. So these are all different products of volcanic activity. So we'll look at each of these. Okay, so the first topic we're going to look at are lava flows. Now again, you're going to have lava flows mostly associated with our basaltic flows, right? Because lava is able to flow in this low viscous type of material, whereas you're not going to really have lava flows with andesitic lava or rhyolitic type of lava, right? Because it's too sticky, it's too thick, it's very high viscous. So you're going to get a little bit of flow, but the andesitic and rhyolitic flows are going to be really concentrated near the source of the volcano. So they're not going to travel great distances, whereas our basaltic flows are going to travel, and they can travel pretty extensive distances depending on how much lava is erupting. Okay, so looking at these different types of basaltic lava flows, you're going to get different types of formations. Okay, so these are, again, mostly with our basaltic lava flows, right? Because, again, andesitic and rhyolitic, they don't really flow. So when you're looking at a lava flow, generally we're talking about basaltic rock and composition, right? Okay, so these can flow great distances. They can flow pretty rapidly. And sometimes they can be associated with lava tubes, which are conduits of lava. So you can imagine that lava is flowing over the ground or maybe slightly below ground. And as the crust around that lava cools, right, it kind of encapsulates the lava flowing through this cooled crust around it. So it actually creates these lava tubes where you have the crust of this recently cooled lava as kind of a shell. And then inside of this tube, you have this flowing river of lava. Okay, so you can actually explore some of these basaltic lava tubes. Here's one. I'm not sure where this is located, but these are really common on the West Coast. I actually was able to visit a lava tube in Oregon where there was extensive lava flows back in the day, long before we were even born. And it's left behind these lava tubes, right? So you can imagine that the lava was rushing through this tube like a river because this lava around it cooled and formed a crust. Okay, so there's these really long networks of lava tubes underground that you can go visit that are now these really just long caves, and they were formed due to lava flowing. Some other basaltic lava flows are Pahoehoe and Aa. So Aa is named because it's a really jagged type of lava flow, and when you step over it, if you're barefoot, it really hurts. It can cut up your feet. So the Hawaiians named it Aa because it hurts. Okay, and Pahoehoe is this type of ropey lava. Okay, so again, lava flows are going to be mostly associated with basaltic lava because the other two types are not going to generally flow in nature. You will get a little bit of a flow, but not much. Okay, so again, with our pillow basalts, we all know what pillow basalts are, right? These are those, imagine squeezing the lava out of a tube of toothpaste, right? These are going to be our pillow basalts. Okay, mostly associated with our divergent settings. Okay, and then you have some columnar joints. Okay, and so columnar joints are when lava cools and cracks in a hexagonal pattern. So these two images are from Giant's Causeway in Ireland, and you can go there. It's in Northwest Ireland, and you see these really beautiful hexagonal columnar basalts. Okay, and these form usually in basaltic flow, but you can get some columnar joints in different types of magma. So this is Devil's Tower in Wyoming, and it's composed of phonolite, which is a more of an intermediate type of lava or magma. But generally, you can see these nice columnar joints in a basaltic flow. We actually have some on the northeast. So there's a lot in Connecticut and some in Massachusetts where you can see, not as beautiful as in Ireland or in other parts of the country, but you will find some columnar joints throughout New England. Okay, again, andesitic lava flows, they will flow a little bit, but not as much, and it'll be really centered around the source of the volcano. Okay, same thing with rhyolitic flows. Any flow that you have with these two types of lava are going to be generally pretty close to the actual volcano. Okay, other types of volcano deposits are volcaniclastic deposits, and these are when volcanoes erupt large quantities of fragments. Okay, so you can imagine that when volcanoes erupt, they explode different types of fragments and material into the air, onto the ground. These can be the actual cooling of different types of lava that are in the volcano. They can also be mixed with the surrounding rock, right? So our volcanoes don't necessarily have to be in an area that's of one composition, right? So our volcano can also be a neighbor to a different type of rock. This type of rock can get incorporated into our volcano. If it gets hot enough, little pieces can break off and be incorporated into the lava, and these can explode when the volcano erupts, shooting all of this material into the air. Okay, typically you don't get this type of pyroclastic debris from basalts, right? Because these are much more runny, they flow, they're not going to produce these really giant explosive eruptions like our other two types of magma, but you will get a little bit of pyroclastic debris from basalts. You will get more of them from andesitic or rhyolitic magma. Okay, they're much more viscous. They contain more volcanic gases, and they explode all of this debris, volcanic ash. You will get this type of volcanic deposit called tephra. You'll also get pumice. These are for more explosive types of eruptions. And then pyroclastic flows are mostly produced in our andesitic and rhyolitic lava, and they're basically hot avalanches of ash, gas, and debris from our silica-rich volcanic eruptions. And these types of pyroclastic flows are extremely dangerous. They travel at incredible speeds, bringing with it very hot ash, debris, gases with it as it travels and barrels down the flank of the volcano. If you are at the base of a volcano or near a volcano when a pyroclastic flow happens, chances are you will not survive it because they travel at incredible speeds and they're very, very deadly. And they incinerate every living thing in their path. So Pompeii, if you're familiar with that story in Italy, these townspeople were at the base of a volcano when a pyroclastic flow formed. They were basically encapsulated and entombed in ash from this flow, destroying the whole town and basically burying a town alive, but first incinerating them all before doing that. Pretty horrendous type of thing to happen. And this is caused by these really silica-rich, explosive pyroclastic flows. Okay, so you can get other different types of flows. I'll just go through volcanic debris flows, lahars. We'll talk about more when we get to geohazards. And then volcanic gas. Okay, so 1 to 9% of magma may be gas. This is controlled by the magma composition. So remember, felsic magmas have more gas. Mafic has less gas. But these gases can be pretty detrimental to humans, plants, animals, depending on how much gas is released into the environment. Sulfur dioxide, carbon dioxide, and then water. These are products of volcanic eruptions. So if you have ever visited a volcano that has some little hot springs, sometimes you can smell rotten eggs because the sulfur dioxide that's seeping up through the ground and releasing these volcanic gases. Okay, architecture. What does a volcano look like? What is it made up of? Okay, so we will have a magma chamber at the bottom, right? This is feeding our volcano, whether it be an explosive or an effusive type of volcano. There's going to be some type of volcanic chamber, okay, sourced from the mantle somewhere. Okay, it's going to have fissures and vents. Okay, so these little fissures and vents can be on the flanks of the volcano here. They can come up through the ground. Okay, these release different gases. They also release little bits of lava at some points here. You can see these little cracks of fissures where the lava can escape, craters and calderas. And then volcanoes have distinctive profiles. So depending on the type of magma, depending on the type of tectonic setting that you will have a different profile of your volcano, so the shape. So we'll look at those two in a bit. Okay, so again, magma chamber. These are, okay, at the base of the volcano. This is the volcanic source. Okay, some of the magma chambers in the world cool completely and give us our plutonic rocks. Okay, so these are nice granite plutons. These were at one point maybe part of a magma chamber that cooled and reached the surface. Okay, they're located in the upper crust. Okay, some magma rises via conduit to the surface. Okay, so these are our fissure eruptions. Okay, little tiny cracks in the ground or on the side, the flanks of the volcanoes. They can evolve into vents where gas can escape. These are just, they look like cracks like this. Sometimes it forms a curtain of fire. So this picture here showing this curtain of fire where we have these fissures, these cracks in the ground or on the side of the volcano where gases and some lava can escape. And they're usually in these linear types of shapes, so little cracks. Okay, so craters are at the summit of the volcano and they're a bowl-shaped depression on top of the volcanoes. Okay, so if you can imagine, mountains have this nice pointy profile, but volcanoes have a little bit of a table at the top. Okay, that's where the crater is. Okay, and these form as erupted lava piles up around the vent. Okay, so there's a central vent at the top of the volcano where the lava is coming out of. The crater is going to be a bunch of just cooled and piled up lava around that vent. Okay, here's an example of a crater. This is Mount St. Helens. This was a terrible volcanic eruption in the 1980s. 57 people died. You can go visit this volcano. It's still active today, but the last time it erupted was in 1980. Okay, so a caldera is slightly different than a crater. So it's a much, much, much larger crater. And they form when a magma chamber empties and the volcano collapses into the space. So you can imagine, again, this is a pain moving my face around, but so you had a volcano at one point. This magma chamber is going to collapse, right? So the material is going to give way and collapse this structure here. And our volcano material is going to fall into the magma chamber that has collapsed, right? And now you're creating this huge, long, wide crater, but now it's a caldera because it's this really huge depression that's in the volcano. And so really good examples of these are Crater Lake in Oregon and Yellowstone National Park. Okay, so whoever has Yellowstone National Park for their projects, you know that it's a caldera. It's a collapsed volcanic chamber. So once upon a time, Yellowstone actually erupted. I think it was 630,000 years ago was when it last erupted. And it was a pretty significant eruption, creating this huge caldera in Yellowstone National Park. Okay, so here's a cool example of a caldera. This is Crater Lake. There's actually two types of volcanoes going on in Crater Lake. You have the caldera, which is this huge lake. So this was a volcano. Mount Mazama was the volcano that it once was. It collapsed, creating this huge caldera. And you can't, I was able to visit Crater Lake a few years ago. It's an absolutely incredible, mind-boggling place. The scale of these volcanoes is absolutely out of control. You can't even fathom how big this caldera is. To imagine that amount of material collapsing basically into the earth is pretty astounding. But if I can find, here's some trees down here on the island. Okay, it's just for some scale, but this is a massive caldera, and this is a collapsed volcano. In the middle of this caldera is actually another type of volcano called the cinder cone, which is what we'll talk about in a bit. But this is the result of the volcano erupting again and producing this different type of volcano. So it's kind of a volcano within a volcano, which is pretty unique. But this is Crater Lake. It's pretty incredible. And here's another example of a caldera in Yellowstone. And you can see some geothermal colors mixing with the bacteria in the hot springs, producing all these pretty colors. Okay, so volcanoes, size and shape. Just check my time. All right, we'll keep it going. You'll have different types of size and shape depending on the magma, right? So again, this large Hawaiian shield is this different type of volcano that's produced from basaltic magma, right? So you can imagine basaltic magma is really runny, it flows great distances, right? So this volcano is going to be really, really a gentle slope. They're going to be much greater laterally, so it's going to go greater distances, but it's going to be not very tall, so elevation is not going to be very tall, and it's going to be really wide. Same thing with the caldera. You can have this large depression that's in the ground. This is typically a nice profile with a collapsed volcano, right? So you can imagine that once upon a time, there was a volcano, maybe at this height, and then it collapsed, sinking into the earth, creating this large caldera. Then you have some smaller, steeper volcanoes, which again can be pretty large, but depending on the lateral extension of the shield volcanoes, they can look a lot smaller, but they actually can grow in great heights. Different types of volcanoes. Now, these types of volcanoes that are much higher and steeper are mostly going to be associated with either intermediate or felsic types of lava or magma, right? Because you don't have a flow when you have these types of volcanoes, right? The flows are going to be concentrated to the actual source of the volcano. So you can imagine that these felsic and intermediate types of magma are going to just build up higher and higher and higher as more volcano is added to that system. Whereas our basaltic magma, when it erupts, it's going to flow out, right, and spill out from the volcano, right? Our felsic and intermediate is going to just stack on top of each other, growing and growing and growing our volcano, right? So these types of volcanoes are going to have a much steeper profile. They're going to be a lot taller. They're going to be smaller at the base, right? Because they're not going to flow laterally, but they're going to just stack on top of one another as they grow. Okay, so these are the different examples of shield volcanoes, right? Our basaltic flows. Okay, Hawaii is a good example. And then our different types of volcanoes like cinder cones, right? So these are small little volcanoes that pile up around the vent of the volcano. Wizard Island is a cinder cone in Crater Lake. You have stratovolcanoes, also known as composite volcanoes. They're large cone-shaped volcanoes. These are mostly made up of felsic lava. Okay, so these again are higher, steeper volcanoes, are going to be mostly felsic to intermediate in composition, right? Good examples, Mount Fuji, Mount Rainier, whoever has that national park, now you know, Mount St. Helens, etc. Okay, so the geologic setting of volcanism, again, this should all be a review. We have convergent settings, divergent settings, and we have hotspots. Okay, and hotspots can either occur in continental crust, like our Yellowstone, or they can occur in oceanic crust, like Hawaii. Okay, and so the reason why Yellowstone, again, is so destructive and so scary is because it's in continental crust, right? And so what does continental crust produce? Really high viscous magma, really, really gassy magma. Okay, so when that sucker is going to explode one of these days, it's going to be really destructive, okay? And it's going to produce a lot of ash. It's going to produce a lot of volcaniclastic deposits, right? Because it is that felsic material. It's in the middle of a continent, right? So that explosion is going to be a lot bigger than, let's say, Hawaii, which is also a hot spot, but it's in a completely different type of crust. It's in oceanic crust, right? So that type of eruption is not going to be anywhere near as explosive as Yellowstone when it blows, right? It's going to be a lot gentler. It's going to flow. Okay, so we have convergent boundaries, right? Our ring of fire, which is where we get all of our really crazy explosive volcanoes. South America, we have our north west corner of America. We have Alaska, right? These are all going to be all nice explosive types of volcanoes for the most part. Okay, but we also have volcanic activity in divergent settings. Okay, so again, these are going to be a lot calmer, not as explosive, but they are going to flow. Mid-ocean ridges generate oceanic crust that covers 70% of the Earth. So we have a lot of volcanic activity associated with these types of boundaries, right? This is what creates our oceanic crust. Okay, so these volcanoes are going to be mostly underwater, but they are going to produce a lot of volcanic activity, right? This is where we get our volcanic crust. Okay, but we also have divergent settings in continental rifts. Okay, so we have one in East Africa that is happening here right now, but we also had a continental rift in New England and on the East Coast. So in New Jersey area, in Massachusetts, in Connecticut, all along the east coast of North America, we had a continental rift similar to what you're seeing in East Africa today. So this is when the continents start to separate and rift. Okay, so you'll also get a lot of mafic material, but you'll also get some partial melting of the crust too, right? Because you're melting some felsic magma. Okay, then you'll get hot spots, right? So again, Hawaii versus Yellowstone. Okay, so I'll let you all read that. And then flood basalts. Okay, so flood basalts happen and they produce a flood of basalt, so to speak. So you can imagine fissures or in divergent settings, the crust is separating and spilling out all of this lava on the surface. Okay, so you'll get large areas of just basaltic flow. Okay, and these are from flood basalts. Okay, and these are usually associated with these specific types of geologic settings when a mantle plume intersects the base of rifting continental lithosphere. Okay, and then we all know and love Iceland. It's a unique place in the world. Okay, you're not only having this divergent setting where you get mid-ocean ridge, but it's also the site of a hotspot. So go visit Iceland if you can one of these days so you can see hotspots and divergent settings in one place. It's insane. Lots of different volcanic activity. Okay, so what are the volcanic hazards associated with volcanoes? Here's a school bus engulfed by lava. Now it's a lava bus. Okay, so what are the hazards? So depending on the volcano, you will have different types of hazards. Okay, so in the previous slide, we saw this bus engulfed by lava, right? These are going to be from lava flows. So you can imagine these shield type of volcanoes. They're going to be runny. They're going to flow like rivers. You can usually outrun them. Most frequently, they're not that fast moving, and you usually have good warning systems involved with shield volcanic eruptions. But if you have immovable structures like a bus, a home, cars, things that cannot move or run, these things are going to be engulfed by the shield volcanic flows. Okay, so that bus is now destroyed. It's now a new type of rock. I don't know what it's called. The stratovolcanoes are going to produce much different types of hazards. Okay, so these are going to be our pyroclastic flows, our lahars, volcanic ash, and debris. Okay, so things you cannot outrun and things that are much more extensive. Okay, so here's a picture of a pyroclastic flow and a car trying to outdrive it, which again, a car can drive pretty fast. These pyroclastic flows can move even faster. So they're extremely deadly, fast-moving plumes of hot ash, debris, and gases charging towards anything in its path. Pretty terrifying. Here is a video of one, I think. Let's see if it'll play. I don't know. Oh, maybe not. Give it a second. See if it decides. Okay, here we go. Maybe. Well, we'll let this go for a second. Let's see if it wakes up. If not, watch it on your own time. It's about It's 3 minutes, so it's pretty extensive. So this is a pyroclastic flow happening somewhere in the world. Okay. It's spinning around. Okay, I will stop this video for a moment and pick up. Oh, there we go. Never mind. We do not have to stop. Okay. Apologies for that. Okay, so watch that video on your own time because my computer doesn't want me to. Lahars. So what is a lahar? Lahar is a bunch of debris, soil, rock, and these are basically these mud flows that happen in volcanic systems where you have a lot of melting ice and rain. So these volcanoes are usually pretty high in elevation, so above the snow line. And these produce a lot of glaciers, a lot of snow on top of these volcanoes. When those volcanoes erupt, that's going to mix with water in these streams from melting ice and rain, creating these really fast-moving and oftentimes deadly lahars or mud flows. Oh, that's my phone. Apologies. Okay, so lahars, pretty dangerous. Okay, ash. So when you have a felsic type of volcano, you can get a lot of ash expelled into the air. Okay, so you have these different types of volcanoes erupting at different points on Earth, creating these huge volcanic ash plumes that are exploded into the air, right? And this directly affects our atmosphere. So these can cause global climate changes. Okay, and then blasts are also volcanic hazards. And this is when the side of the volcano erupts instead of the summit. And these create this huge blast similar to like a bomb or an explosion. Okay, and you can see all of these trees that were blown over or blasted by this volcanic eruption. Okay, and then landslides are obviously something that can happen with volcanoes. When these rocks, when the slope fails on these volcanoes, you can get a bunch of different landslides and rock falls. Mount St. Helens is a really good example of as many geohazards as you can think of. So landslides, lahars, blasts. This was an extremely violent volcanic eruption where a lot of terrible, destructive things happened. It's amazing that more people did not die in that eruption because it was so severe. You also have tsunamis. So again, when you have these giant volcanic eruptions, they can sometimes create tsunamis. This is from earthquakes usually. So sometimes volcanic eruptions can trigger an earthquake, which can trigger a tsunami. Or if you're getting a large amount of volcanic debris being deposited into the water rapidly at once, the water will accommodate that influence of material by a tsunami. So sometimes you get tsunamis with volcanic hazards. One in 1883 actually killed 36,000 people. This is in the Indonesia region of Java or Sumatra, caused by a volcanic tsunami. Okay, and then the last threat that we have, I think, is gases and aerosols. So again, you have a lot of gases being expelled into the air when you have this mostly felsic type of lava erupting, but you get it with every type of lava or magma, okay? But felsic, you'll have more gases. Okay, and so what are the effects of volcanic eruption in Earth's history? Okay, so we've had pretty significant climate effects based on volcanic eruptions. Okay, so this is enough to alter climate. So ash and aerosols get expelled into the air, high into the air. They block sunlight and they initiate an atmospheric cooling. So 1815 was known as the year without summer, and this was due to the eruption at Mount Tambora. Okay, and this, I believe, here is a map view of where Mount Tambora is in Indonesia. and it was the worst famine of the 19th century, and snow fell in Albany in June. Okay, so this directly impacted climate in 1815 because of this very violent volcanic explosion, inputting all of this ash into the atmosphere and starting this global cooling. Okay, so here's another diagram of that. You have evidence of these happening at much ancient points in our Earth's history. So about 250 million years ago, we had an extinction event caused by this volcanic eruption erupting all of this gas into the atmosphere and causing this pretty significant extinction event. 96% of all marine species and 70% of all terrestrial vertebrate species becoming extinct because of these really toxic gases into the atmosphere, as well as the ash that was in the atmosphere, creating this cooling in the climate. Okay, and so here's a nice diagram of volcanic history and the comparison between the different volcanic histories. So you can see Mount St. Helens in 1980 was a very severe volcanic eruption for our time, but compared to other volcanoes in history, it's pretty small. So I mentioned Yellowstone, okay, 2 million years ago is when it erupted. Oh, it erupted several times. Okay, so 630,000 years ago it erupted, but there was a much larger eruption at Yellowstone 2 million years ago, which was the largest eruption on record for Yellowstone. But the most violent eruption was in Indonesia. Okay, so our conversion plate boundary winds expelling all of this material into the earth, creating this huge, large, violent eruption because of a conversion boundary. Okay, and these are called supervolcanoes. Okay, so here's a couple of slides on volcanic history. So Mount St. Helens, I'll let you all go through that. Krakatoa, again, was in Indonesia region. And then Pompeii. So this was in Italy, right? And these are the poor people that were entombed by the ash. Volcanic ash welded these people basically in place. So you can see a little boy and a dog at the Pompeii Museum, really decimating this poor city in Pompeii because of Mount Vesuvius. So geologic hazard frequency, what can we do to mitigate geologic hazards? It's very hard to tell when a volcano will erupt. Same with earthquakes, very hard to predict. More frequently, you'll get some volcanic activity like hydrothermal explosions. So in Yellowstone, it has very frequent geyser eruptions. Okay, this is when steam is erupted from different parts of the volcanic system. You'll get some earthquakes, you'll get lava flows, and then caldera-forming eruptions do happen, but the more destructive the hazard, so these really violent eruptions versus these small hydrothermal explosions, okay, the more destructive something is, the less frequent it's going to occur, right? Because you need a lot of energy to be built up over a long period of time for these types of events to occur. Okay, so they don't happen as frequently as they are more destructive to us and our climate. Okay, but we can predict them on some extent based on recurrence intervals. So it's the same type of way we can predict our earthquakes. We can look at the Earth history and see when these different volcanoes erupted and how far apart these eruptions were. And we can kind of predict when the next one will be based on how far apart these volcanoes erupted. Okay, so it all depends on data. We can also look at INSAR, so satellite radar data, to use elevation. Color bands indicate the amount of movement between the times. Okay, so this will track the movement of the volcano, looking at different types of volcanic activity. So if you have earthquakes or lava flows or any type of different volcanic activity, you can track that and kind of predict when our really big destructive earthquakes are going to happen based on that type of activity. Okay, you can also have mitigation geologic maps showing which areas have the most likely recurrence interval based on where they are located. And if you're asking yourselves, why would people build cities and civilizations at the base of volcanoes? They explode, it's terrible, these people die, the cities are ruined. Why did they do it? Well, a reason why most of these civilizations build near these volcanoes is because volcanic soil is actually extremely fertile. It holds nutrients extremely well. It's a good aerated soil, nutrient rich, and so it's very easy to grow crops at these bases of mountains, volcanoes, because of how fertile the soil is. So many times these civilizations will build right at the base of a volcano because the soil is so fertile and it's easy to grow crops on. So if you're wondering why people keep doing this over and over and over again, there's a reason, and it's because of the resources available due to this volcanic activity. So great damage can happen, but you can also grow a lot of very healthy, nutrient-rich crops based on this type of volcanic activity. And if you're thinking that volcanoes only happen on Earth, you would be incorrect. Okay, there's volcanic activity happening on other planetary bodies. Okay, so volcanic activity happens on the moon, it happens on Mars, and it can also happen on other planetary bodies like moons on Saturn. So Io experienced the moon on the moon on Saturn experiences volcanic activity. Olympus Mons is a volcano on Mars. You can go visit it on Google Earth, and it's 3 times the height of Mount Everest, and it is an extinct Martian shield volcano. So you can imagine a shield volcano is mostly basaltic lava, right? Same type of deal as Hawaii, but it's 3 times the height of Mount Everest, which is insane. So as you all know from this lecture, these shield volcanoes don't typically grow as high because they are runny basaltic flows and they go great distances. So you can imagine that this Olympus Mons is 3 times the height of Mount Everest. So you can imagine how long this volcano had been accumulating this type of lava and magma for it to grow 3 times the height of Mount Everest. Mars also doesn't have the same types of geologic processes as Earth. So there isn't the same type of weathering and erosion breaking down the volcano and carrying this material away. So you can imagine that these volcanoes on Mars grow to incredible heights based on its different type of tectonic activity from Earth. Okay, so these are the different types of volcanoes you can have on planetary bodies, and you can visit them on Google Earth. I think that's all I have. So with that, I will end, and please look at these videos on your own time because they're really cool. Okay, thank you all for listening.